Hello, we are here to present our work, MobileBrick, Building Lego for 3D Reconstruction on Mobile Devices. This is a multi-view RGBD dataset captured using a mobile device, which includes highly precise 3D ground truth annotations for 153 object models featuring a diverse set of 3D structures. We obtain precise 3D ground truth shape without relying on high-end 3D scanners by utilizing Lego models with known geometry as the 3D structures for image capture. The distinct data modality offered by high-resolution RGB images and low-resolution depth maps captured on a mobile device, when combined with precise 3D geometry annotations, presents a unique opportunity for future research on high-fidelity 3D reconstruction. Obtaining precise 3D shape annotations to evaluate 3D reconstruction algorithms has been a challenge. Even annotations created from high-end LiDAR scanner can introduce artifacts, as shown in the figure here. Instead of using 3D scanner to obtain 3D shape annotations, we create annotations by building a digital replica for each object in MobileBrick, such that the annotations are highly precise for objects captured in the videos. We not only obtain accurate 3D shape annotations but also specifically target mobile applications when capturing MobileBrick. Unlike other 3D evaluation benchmarks that are captured under controlled setups, MobileBrick is captured using an iPhone equipped with a built-in LiDAR sensor. The capture setup for MobileBrick closely resembles how most customers would utilize their smartphones to capture 3D models. This allows us to gather a distinctive dataset comprising high-resolution RGB images accompanied by low-resolution depth maps. This presents the opportunity to investigate how to effectively use low-quality yet easily accessible depth maps in 3D object reconstruction. There are three major steps to construct the MobileBrick dataset. The first one is capturing RGBD image data using an iPhone. The second one is building a digital replica for objects captured in the videos. Lastly, we align the digital models to the image sequences. We record video clips on an iPhone moving around an object of interest. ARKit provides high-resolution RGB images at 1440 by 1920 pixels and low-resolution depth maps at 192 by 256 pixels. It also outputs both the extrinsic and intrinsic parameters of each frame. There are two types of 3D models in the dataset that can be categorized as real-world model set and random model set depending on how a model is built. The real-world model set refers to official Lego models that are created by human designers. The digital models in this category are available on Lego modeling websites, such as L-Draw or MobileBrick. Since the number of official Lego models is limited, we augment the MobileBrick dataset by using procedural generation to create a large amount of digital Lego models using 72 primitive Lego bricks randomly. We can also modify the digital models if needed using the BrickLink Studio. The most important procedure for building the MobileBrick dataset is aligning a digital 3D model to an image sequence, so that the aligned model can be used for evaluation. We devise a human-in-the-loop alignment process. In the first PNP alignment step, the annotators are asked to annotate 10 to 23D keypoints and their projections on an image given the user interface. The digital model is roughly aligned to the image sequence after this step. Since acquiring pixel-perfect correspondences is difficult, it is necessary to further refine the object pose. We provide a user interface that shows the projections of the 3D model to 8 different views uniformly sampled in the image sequence. The annotators can adjust the 6-degree freedom (DOF) transformation parameterized by 3DOF translation and 3DOF Euler angles, such that the overlap between the model projections and the object foreground in the images is maximized. After the manual alignment steps, the digital model is aligned well with a subset of image frames. To propagate the object alignment to the rest of the sequence and rectify the camera drift caused by ARKit, we refine the camera poses by minimizing reprojection errors. We first evaluate the quality of the proposed dataset and the alignment process. To evaluate the pose alignment, we record 10 calibration sequences, where a randomly selected LEGO model is put on a calibration checkerboard. We then use the camera calibration algorithm in the OpenCV library to compute the reference camera poses for evaluation. We report the pairwise root mean square error for translation and degree difference for rotation in the table shown here. Despite the ground truth shapes theoretically are the replicas of the actual objects used for image capture, shape errors still exist in the model construction process. To investigate the effect of accumulated error of model building, we measure the 3D dimensions of 20 models randomly selected from the dataset using a micrometer with an accuracy of 0.05 mm. The difference in average is 0.2 mm. We investigate the performance of a wide range of multi-view reconstruction algorithms with different types of input data. Voxsurf achieves state-of-the-art performance, outperforming traditional MVS, learning-based MVS and depth map fusion approaches. MVS solutions, compared to neural field-based approaches, are penalized heavily in recall, as they struggle to reconstruct homogeneous regions where texture is insufficient for MVS. Although depth maps are beneficial in large-scale 3D reconstruction, such as reconstructing a living room, the low-resolution depth maps on mobile devices fail to capture geometry details of objects, which causes methods relying on depth maps perform the worst in this experiment. To summarize, we present MobileBrick, a dataset consisting of a diverse collection of 3D LEGO models and the precise 3D ground truth annotations associated with RGBD image sequences captured on a mobile device. We anticipate that our dataset will provide a valuable resource for researchers investigating multi-view reconstruction using RGBD images from mobile devices, and we believe that our benchmarks will serve as a critical evaluation tool for assessing progress in this field. However, we acknowledge that the uniform surface property of LEGO bricks can be a limitation of our dataset, which can be alleviated by applying various types of paints on the models in future work. Please come to our poster and visit our website by scanning the QR code for more details.